So this is part 4 of Unit 1, where we will talk now about wave functions and quantum numbers and orbitals. So wave functions can be expressed in three-dimensional coordinates. We can have Cartesian coordinates, x, y, and z, and we can have spherical or polar coordinates, r, phi, and theta. Okay, so let me just show you on the diagram. You can see over here we've got the z-axis that points up, the y-axis that points to the right, and the x-axis which sticks out of the plane of the page. Okay, and then if we were to define a point somewhere over here, okay, let me just circle it. Oh, sorry, this point here. Okay, you'll see that it will have x and z coordinates at that point. If we looked at this point here, we will see that we have x, y, and z coordinates at this point, where the z will be in the negative direction. Okay, if we had to extend this down here. All right, now I want you to imagine that this position that I've just drawn over here also fits on the surface of a sphere. Okay, and that has a certain radius from the center of the origin. Okay, so it has radius r, okay, over here. So wherever we go from the center to the outside of the sphere, the value of this line over here would have the value of r. Okay, so that will have a certain angle, theta. There's that angle there. And it will also have an angle phi. Okay, so the angle theta is the angle from the z-axis, and the angle phi is the angle from the y-axis in this case. So we're looking at the position then, any position of anywhere along the sphere. Okay, so theta is measured along the arc, okay, which is shown on the diagram. And at that particular position over here, we'll have the coordinates, polar coordinates of the radius, the theta angle, and the phi angle. Okay, and at this point, we talk about radians. So the position here, this point here, sorry, that is defined as theta is equal to 0 radians. Okay, and this point over here is defined as phi is equal to 0 radians. Okay, so the point of this whole exercise is that we can position any point, any position of an electron along an orbital to have x, y, and z coordinates and spherical coordinates, polar coordinates. Okay, as a result of this, we can then determine the atomic wave functions for 1s, 2s, and 2p orbitals to have different values. Now, what you see in the table over here are the three quantum numbers that you are familiar with. So n is equal to 1, L is equal to 0. Remember, the condition for the L quantum number is n minus 1. And then the magnetic quantum number has values that are 0, it's minus negative, and negative L and positive L. Okay, so in this case, ML is equal to 0. Okay, this part of the table here shows the radial part of the wave function. So calculating the position along the surface of a sphere, and then the angular part of the wave function is given over here. Once again, I don't expect you to know this table and to know these formula, but I do expect you to know what the 1s, 2s, and 2p orbitals look like. Okay, so let's get on to that. So if we had to plot the radial function versus the distance from the nucleus for a 1s orbital, you would see that this diagram on the left over here shows the wave function. Okay, and the diagram on the right shows a similar kind of wave function for the 2s orbitals. So this here is for 1s, and this one here is for 2s. Okay, so that's what the wave functions look like. If we had to solve the Schrodinger wave equation and plot it on a Cartesian graph, this is what the mathematical functions would look like. Okay, if we had to do it for a whole host of orbitals, we can see that the green line shows us what the 2p orbital looks like. The pink line shows us what the 3p orbital looks like. The black line what the 4p orbital looks like. And the blue line shows us what the 3d orbital looks like. Remember, these are wave functions. Wave functions describe the shape of the orbitals. Okay. And this is what we would see for 1s, 2s, and 3s. So what you will notice is now what we're going to do is we're going to take a look at these wave functions by, if I was to look down, okay, so if I have to draw an eye like this, I'm going to look down. This is what I'm going to see. So for a 1s orbital, hold on, I just need to find my pen. Okay, so a 1s orbital has a wave function that looks like this. If I'm looking down, can you see? I see a sphere. Okay, so I'm plotting a three-dimensional sphere. Okay, if I look for a 2s, this is the green curve on the right, you will see that I have a node over here. So this is where the nodes come from. There's a node right over there. Okay, so we have a little bit of density in the middle, and then the majority of the electron density is on the outside over here. And then we've got two nodes for a 3s orbital. There's a node over here, and there's a node over there. And so you will see two nodes. There's the one node, there's the second node. That's what the 3s orbital looks like. And that's how we define the shapes of the orbitals. Okay, here's some more wave functions for a 3D in green, a 3p in the red, and a 3s orbital. Okay, and obviously if we look down at what they look like, we'll get some indication of what the orbitals are going to look like. Okay, another representation of the orbitals. So at the bottom we have the 1s, here we have a 2s and a 2p, and at the top we have a 3s, 3p, and a 3d. Okay. All right, so with the principal quantum number, we know that n is equal to 1, 2, 3, or 4. It determines the energy of the electron in a 1 electron atom, for example, and indicates approximately the orbital's effective volume. So that is how we end up with a n equals 1. We've got 1s in this case. It's a spherical orbital. So this would probably represent a 1s orbital. This one would represent a 2s, and this one would represent a 2p. Okay. For the angular momentum quantum numbers, that's going to determine the number of nodal surfaces, so where the wave function is going to be equal to 0. So we know for L equal to 0, 1, 2, 3, and 4, in other words, n minus 1, we know that L equals 0 is an s orbital, L equals 1 is a p orbital, L equal to 2 is a d orbital, and L equal to 3 is an f orbital, and so on and so forth. So if we looked at the pictures down the bottom here, this is how we can describe the s orbital shape. It's a spherical shape. And then the p orbitals, there are 3 of them. Okay, remember that this is described by ml to say there are 3. We have one in the x direction, which is this one over here, and there is a positive section of the wave function and a negative section of the wave function in the x direction. This one here is the py. Again, we have a negative section of the wave function and a positive section of the wave function, and then we have the pz orbital, which is the positive section above and below the y-axis. Okay, and there are 3 of them because of the quantum numbers, as you've seen in previous times. Okay, so If we looked at the d orbitals now, there are 5 of them. Remember that we have L is equal to 2. That means ML is equal to 5 different combinations, -2, -1, 0, 1, and 2. Okay, so we have the dz squared. That's the first orbital, this one here. Then we have the dx squared minus dy squared over here. And then we've got the dzx at the bottom, the dyz, and the dxy. And you'll say to me, Prof, what is the difference between the dx squared minus y squared and the dxy orbital? I could ask this kind of question. If you look quite carefully, okay, so this is the y-axis over here. Oopsie, sorry. That's the y-axis. Oh, come on, this pen. That's the y-axis. This is the x-axis. You will see that the lobes of this particular orbital actually go through the axis. Okay, so you have a look at this brown portion of the orbital. The orbital is along that specific axis. And similarly with the x part of the x, along the x-axis, you have the lobe intersecting or cutting through the x-axis. Okay, if we look here at the dxy down the bottom right, you will see that the lobes are in between the axis. Here is the y-axis here, and here is the x-axis here. The lobes are in between the axes, so that's the difference between the orbitals. All right, so you should know how to draw these. If I say to you, please draw one of the d orbitals, I would expect you to know how to do that. Okay, and on the next slide, we will see the f orbitals. These are obviously a whole lot more complicated, but you can get an idea of what the wave functions look like for these orbitals in the x, y, and z direction. So these will be the solutions to the Schrodinger wave equations, which give the wave functions for these particular orbitals. And these would have, because they're f orbitals, the L quantum number would be equal to 3. Okay. So, for many electron atoms, how do we define it? It's any element that's got more than one electron. Okay. We're going to use something called orbital approximation, where each electron is going to occupy an atomic orbital that's going to resemble those that are found in a hydrogen type atom. This occupation is obviously described by the corresponding wave function and set of quantum numbers. We're then going to apply the Pauli exclusion principle. I refer you to first year chemistry and ask you to refresh your memory in that regard, where no more than 2 electrons can occupy a single orbital, and if they do occupy a single orbital, then their spins have to be paired. So remember that one electron spin must be upwards, where the spin quantum number is +1/2, and the other must face downwards, where the spin quantum number is -1/2.